Hi everyone! In this series of videos we're going to be solving exponential and logarithmic equations. This first video is just going to go through some basic examples that only require about one step. But before we get into the examples, let's just talk about the two main tools that we'll use to solve exponential equations. The first one, we've already seen both of these before, but I'll just remind you of what they say. The first one is the one-to-one property. So for exponents, that says that if I have a to the x equals a to the y, so same base and different exponents and they're equal to each other, this is exactly the same as saying x equals y. So from the left-hand side, a to the x equals a to the y, we can conclude that x equals y. We have a one-to-one property that also holds for logarithms. So that one says basically the same thing. If I have log base a of x equals log base a of y, then x equals y. And so again, we often use ln, the natural log. So with ln, we just have if ln x equals ln y. This is the same as saying that x equals y. So that's how the one-to-one properties work, and we'll see a couple of examples of them in action helping us to solve a couple equations. The inverse properties are possibly, arguably more important because they work in any case. The one-to-one properties you may not always be able to apply. And what the inverse property for exponents says is that a to the log base a of x simply equals x. And on the logarithm side, so for the natural log, that we'll have a base of e. So that's e to the ln x equals x. And it basically just says if I compose the action of raising to the power of x with the function log, I will just get x. So they're inverse operations, which means I can compose in the other order. So if I take log base a of a to the x, I'm just left with x. And in terms of the natural log, that looks like ln of e to the x equals x. So let's now see how we use these properties in a few simple examples. So here's our first example, 2 to the x equals 32. So in order to do this, I'm going to rewrite 32 with a base of 2. So on the left-hand side of the equality, I have 2 to the x. 32 is the same as 2 to the 5. So I have same base, different exponents. So by the one-to-one property, those exponents must be the same. So x equals 5, and the property we've used is one-to-one for exponents. Let's look at another example. I have ln x minus ln 3 equals 0. So you might be able to see already that I probably want to use the one-to-one property because I have two logs of the same base, and I'm trying to solve for x, which is inside of the log. So my first step will again be to rewrite and just say ln x equals ln 3 by bringing that term over. And now I can use the one-to-one property for logs. If I have ln x equals ln y, then x equals y. So that tells me x equals 3. And I've used the one-to-one property again. The third example is a little bit trickier because it's not so obvious what the base should be in order to use the one-to-one property. But I can rewrite it so that this has base 3, because you'll remember that 1 over 3 is the same as 3 to the minus 1. So the left-hand side I can rewrite as 3 to the minus x, and 9 is a power of 3, it's 3 squared. So I have same base, different exponents. I can conclude the exponents are the same. So minus x equals 2, or in other words, x equals minus 2. And again, I've used the one-to-one property. So let's move on to a few examples where we use the inverse property. So I have e to the x equals 7. I know that I can't use the one-to-one property because there's no nice way to write 7 as e to some power. That power is not going to be easy to interpret. So what I can do is I can use the fact that ln of e to the x equals x. I do this by taking the ln of both sides of this equation. So when I do that, I'll have ln of e to the x equals ln of 7. So since I've taken the ln, I've taken the natural log of both sides of the equation, I haven't changed the equation. Now, by the inverse property, ln of e to the x, the left-hand side, we know that this is just x. And the right-hand side, we can't simplify anymore, so that stays as ln 7. So that's my solution. X is the natural log of 7, and I've used the inverse property here. Let's try another. So now I have ln of x equals negative 3. So this isn't written in terms of the natural log like my example up here. So I need to use the inverse property again. But how will I do it this time? If I take the ln of both sides, that's not really going to help. But I have another form of the inverse property. If I have e raised to the ln of x, that equals x. So what I'm going to do might seem a little bit funny, but it's a very, very common practice in math that you're going to have to get used to. It's called exponentiation. And what it means is each of these sides will become the exponent, and I'm going to choose my base to be e, the same as the base of this log, so that the inverse property will apply and the x will, and everything except the x will just go away. So I'm going to, some people call this e-ing both sides. So now I have this expression, e to the ln of x equals e to the minus 3. But by the inverse property, e to the ln, those are inverses. So on the left-hand side, I'm just left with x. And on the right-hand side, I can't simplify that anymore. So I have e to the minus x. And that's my solution. So let's do another example with this property of exponentiation. Here I have log of x equals negative 6. So you might remember that when I just write, or equals negative 1, write log, that means base 10. So in order for this exponentiation process to work, I need the base of the exponent to be the same as the base of the log so that the inverse property will apply and everything will cancel out. So since this is log base 10, I exponentiate by putting a base of 10 on each of these and making that the exponent. So I have 10 log base 10x equals 10 to the minus 1. Now the inverse property applies on the left-hand side, so x equals 10 to the minus 1. So I would say these last three examples are the very most important. Here we had to take a log of both sides in order to apply the inverse property. In the next two examples, we used this process of exponentiation, where both sides of the equation became the exponents and the base was chosen to match the base of the log so that we could apply the inverse property. So study these examples really carefully because they're the base for the more complicated examples that we'll do in the next couple of videos. So good luck on the web work and let me know if you have any questions.